In our last lesson, we looked at some operations with algebraic vectors, including vector addition as well as scalar multiplication. So my question is here, well, can two vectors be multiplied? Well, sort of. We're going to learn two different methods of multiplying, and they do two different things. One's called the dot product, which is the focus of this lesson, and the other's called a cross product. Now, to denote a dot product for two vectors, so let's call them u and v. So here's vector u. When we dot it, we actually use a nice solid dot in between, and v would be here. So we don't use the times sign, we use an actual dot between the vectors, and that has a specific meaning. Versus a cross product, which is u with the x for the multiply, or the cross, and v. So these are two different types of multiplying that we do with vectors. Now, you need to make sure that you understand how these work, because it's not just any other multiplying like you would with a scalar. So I'm going to relate this to some physics here. Work in physics is the energy transferred to an object when the force acting on the object moves it through a distance. So what we have with that is that work, W, capital W for work, is our force multiplying our displacement. Force multiplying displacement. Now, when we talk about vectors, this force is in newtons and displacement is in meters. So Newton meters, or we use the unit joules, so measured in joules. And we denote that with a capital J. All right, so we're going to work with that and look at how that goes with our vectors that we've been talking about. Sometimes in physics you might also see this force as a capital F, a force vector, times, and it has a dot as a times, and then your d vector, your displacement. All right, so for our examples below, the u is representing our force and our v represents the displacement, if you want to think about that. So they are both heading in exactly the same direction. So when I go to find my work, the work here is going to be the most efficient I can do because I'm pushing or pulling in the direction that I want to actually move that object, and I want to move it 5 units. So my work is actually 3 times 5, which is 15 joules. Okay, and as I said, it's the most efficient way we could do this because we're moving that, pushing or applying that force in the direction we want to move the object. So now for this next example, my force is actually being applied upward at an angle here. So I might be pulling a wagon, but I want to move it forward. So I do have that upward force, but overall, when I look at the force that actually moves the object, the force that moves the object is just the horizontal component of that overall force, which has a magnitude of 3. So this isn't quite as efficient as the previous example. We need to take into consideration that the actual, I'm going to call this x, the actual horizontal force that's moving that object would have to be calculated in relation to the angle theta, the angle that those two vectors originally are making with one another here. So if I think about my cosine and the fact that this is my right triangle, I could figure out that my x, the magnitude of the x, divided by the magnitude of the hypotenuse, which is the magnitude of my u, that is equal to the cosine of the angle. So my x is actually equal to, or the magnitude of x is actually equal to the magnitude of u times the cos of the angle between vector v and u. Okay, so I'm going to have to factor that in. So my work is not going to be 15 joules this time. It should be less than 15 joules. So I've just added in the fact that the part of the vector that moves the object forward is the horizontal component of the vector, and I've also added the fact here that our theta is going to be between 90 and 0 degrees here. So this will still be okay for moving the object forward. It's just not as efficient as our option up above. All right, so now we're going to look at the case where my force is being applied in an upwards direction. So we've got this vector happening here, but we want to move it forward. So if you think about that, you want to move something forward, but you're either pulling upwards on it or pushing upwards on it. That actually isn't going to move your object. So we're going to end up with no work being done here at all. I mean, you're putting in effort, but you're not actually accomplishing the goal of moving the object. So overall, our work is going to end up equaling 0. Okay, you're putting effort in, but you're not actually accomplishing anything. If we look at the next example here, my theta is between 90 degrees and 180 degrees here. So what's actually happening is we're pulling or pushing in the opposite direction and up at an angle to what we actually want to move that object in. So in fact, we again are looking at that horizontal component, and it's actually going to be in the reverse direction. It's going to be a negative direction here for our horizontal component. If I looked at the horizontal component on the previous one, my horizontal component would actually be a 0. So I'm just going to add that in here. The horizontal component would actually be equal to 0 because it didn't move left or right at all. This one's going to be negative. But again, we could figure this out. We could take the cosine of our theta, and that will equal the magnitude of that horizontal vector divided by the magnitude of the actual vector itself, the horizontal component. So that means our, I put H for horizontal there. That means our magnitude of that horizontal component is still going to be the magnitude of vector u times the cos of the angle. Now, if you remember from your work with cast rule, cosine will be negative when we are in that second quadrant. So when our angle is between 90 and 180 degrees, it will give us a negative value. So what's going to happen overall here is this will be a negative value. So our work will actually be negative. We're working against where we want to go. All right, we're going to look at the next example here, and the last in our chart. I have a vector now. We're actually pulling in the opposite direction that we want to move it. Okay, we want to move it forward, but we're actually going to the left by 3. So again, we are moving that object in the opposite direction, and it's not going to move it forward at all. We're going to end up with exactly negative 15 joules of work here because we're going in that negative direction. So our work here will equal negative 15 joules. Okay, and that's because our magnitude of the x vector, of the x component, would actually be equal to the 3, but it's going to be, as I said, we're working against the direction we want to go in. All right, so how does this all work out here? I want to go back to the original example up here. It looks like work should just be the product, based on our information here, the product of our force vector with our displacement vector, which was true with the very first one. 3 times 5 is 15. The issue with the second one, when I go to calculate work, and maybe I'll do this in a different color, our work really is the magnitude of our x vector, the horizontal component. Now the horizontal component really is this, and we want to multiply it with the displacement vector's magnitude. So if I look at the displacement vector's magnitude multiplying, these are just scalar values, so we can just multiply as we would normally multiply, times the magnitude of u times the cosine of the angle between them. Let's say, let's let theta equal 30 degrees, just because. Okay, so vector v's magnitude is 5, vector u's magnitude is 3, and we're going to do the cosine of 30 degrees there. Now when I put that in the calculator, we should get an answer that's less than 15, but still positive. So 15 really times the cosine of 30, and that gives me 12, almost 13 joules there. I'm going to round that to the nearest whole because 12.99 is what my calculator said. So approximately 13 joules. So it's still pretty good. It's not as efficient though as pushing straight ahead. Now, how does that fit in with our next example of the 90 degrees? So our work is our magnitude of our one vector times the magnitude of the other vector. It doesn't matter what order I put those in because they're just numerical values, scalar values that get multiplied together, times the cosine of our angle. So in this case our angle is 90 degrees. So when we do 3 times the 5 times the cosine of 90, the cosine of 90 equals 0. So we end up with 15 times 0, which is 0. So that's why our work is 0 in this calculation. So it's the cosine of the angle that helps us get the actual amount of work. Now let's say our theta in this example, theta, let's let that be 120 degrees. Our work here then is still the magnitude of our two vectors, our force vector and our displacement vector, and we're going to multiply it by the cosine of our angle. We're going to have our 5 times, sorry, that was supposed to be 5 times 3 times the cosine of 120 degrees. So 15 times 120 cosine, that is a negative, and that gives me negative 7.5. So our work here is negative because we're not moving in the direction we wanted it to move. We're actually moving it in the opposite direction to where we wanted it to go. So that statement will be true for both of these last two examples here. So this time, if I look at my theta, oops, I moved those and I didn't mean to. Let me get what I want for my toolkit here. My theta, my angle here, is 180 degrees. So the cosine of 180 degrees, if you remember the cosine curve, is actually going to equal -1. So when we calculate the work on this one, we're going to take the magnitude of our one vector times the magnitude of our other vector times the cosine of that angle between them. And this will be -1, which gives us -15 joules. So it is the most inefficient way of trying to move that object because it's going to end up in the complete opposite direction to where we want it to go. So overall, we have a rule for our dot product, which I'll put on the next slide here. So I've summarized how to find the dot product for geometric vectors. So the ones we were just working with were geometric. I didn't have them on a Cartesian plane. To get the dot product of our two vectors, it's the magnitude of the one times the magnitude of the other times the cosine of the angle between them. And remember, the angle between any two vectors is when those vectors are joined tail to tail. So just keep that in mind. That's always by definition how we define the angle between two vectors. Another key concept to get out of that little investigation is if your dot product was or is equal to 0. That happened exactly in the case when our vectors were perpendicular to each other. You'll notice that. That's because that cosine of theta is 90 degrees. So that dot product will always be equal to 0 if theta is 90 degrees. The opposite to that is true as well. If you know your angle between your two vectors is 90 degrees, then their dot product has to equal 0. So those are all our key ideas out of that. You've got positive versus negative work as well. But what you should also notice about the answers is that they're always scalar values. The dot product will be sometimes called the scalar product as well. Dot product and scalar product mean the same thing. So see if these things make sense here. Do they give scalar quantities? Do they give vector quantities? Or do they give undefined results? So take a look through those. See what you think here with the 4 examples, and then I'll take them up on the next video.